morning, my name is Jay Jesus,
My name is Ashish Singh.
and we're here to present to you our MeJPass32 MIPS processor. Let's begin by why the name. MeJPass32 is an acronym, M stands for MIPS, E enhanced, J Jesus, P Perez, A Ashish, S Sin 32-bit. So what is a MIPS? A MIPS is a 32-bit processor which is organized into two major parts. You've got your control and your data path. Your control is in charge of instruction detection and memory interfacing. Correlates the signals which will be necessary for the data path to flow for its corresponding instruction. For the data path, executing the instructions is necessary to execute the instructions. It's the interconnections of the internal units in order to perform the instructions as needed. So our MIPS instructions are divided into two major parts. We've got our baseline MIPS instructions and we've got our enhanced instructions. What we did for enhancement was 4 R-type enhanced instructions and 2 modified J-type instructions. Here we can see the baseline for the MIPS instruction set, which are R-type, I-type, and J-type. And here's some common instructions for those types of instruction styles. Below you can see the instruction formats for an R-type, I-type, and a J-type. Furthermore, we've got our enhanced instructions, which Ashish will discuss.
Okay, so all we really did was we created a few more R-types that are not native to MIPS. We'll talk more in detail on what they are actually. We have the NOT, the NAND, the XNOR, and the squared that I thought of would be kind of cool. And then the other one is the J-type is the jump on carry and jump on not carry that was not native in the instruction set. So essentially what we're doing is we're looking at an enhanced key. We're looking at bits 26 through 31, and we're looking for a 1F in there. And once we have the 1F in the decode state, we're going to be checking bits 0 through 5, and later on we're going to show in our state machines how we picked what we picked the values to be to execute these instructions. Please stop us and ask us any questions if you have any.
So what is a 32-bit processor? MIPS is a 32-bit processor because it's got 32 different registers, and each register is 32 bits in length, which means that our operand's operating with 32 bits. Some unique registers to keep in mind from the MIPS is register 0, which is hardwired to a value of 0, register 31, which is our return address register, and register 29, which is our stack point. And now that we've introduced the MeJPass32, we're going to move on to hardware.
So this is our block diagram of how our processor is organized. Right on top you're going to see the CPU test module. Now this is the wrapper, this is our test bench. Okay, this will instantiate the CPU module and the 2 memory modules. Okay, we have the data memory module, we have the input-output, which is also a memory module. And inside the CPU we have three other modules. You're going to see the control unit, the instruction unit, and if you notice the instruction unit also has a memory module in there for the instructions. And then we have the integer data path, which has the registers and does the number crunching. We'll get in details on each one.
So to summarize what Ashish said, here's a top-down style of our design. On top you've got your CPU test module, which is our test bench. And what that does is it verifies the functionality of our 3 units under test, which is our CPU module, data memory module, and our input-output module. Within the CPU module, you will find the control unit module, the instruction unit module, and the data path module. Within the instruction unit module, you will see the instruction memory module. Now these are just thumbnails. We will zoom in so you can see the internals and discuss more about it. So CPU test module, what is a CPU test module? That's our test bench. This is how we verify that everything is working. The purpose is to simulate and verify the design. What it does is it asserts a reset and kicks off the finite state machine. It includes some tasks, and those tasks are used for dumping the PCIR and register values, which we can then use to verify the outputs to make sure everything is correct. So
here's the CPU module. Again, this is an overall block diagram that we extract it from the Xilinx tool. On the left-hand side, you're gonna see all the inputs. On the right-hand side are the outputs. Okay, and within the CPU module, as we discussed earlier, we have three major modules. We have the control unit, instruction unit module, and the data path module. Let's talk a little bit about the control unit modules. So this module is in charge. It's a finite state machine. It's a Moore state machine. And it keeps track of every single control signal at every single clock. Again, on the left-hand side are the inputs, and the right-hand side are the outputs. And we will give you a screenshot of our finite states, or some of the states, actually. This is the instruction unit module, which is really residing on top. It's in the fetch state. It's taking all the instructions. It's also in charge of where the PC is getting updated on every clock. And this third unit is the data path module. This unit actually has your registers that are organized in there, and also your ALU. Notice to access the registers, we are going to need some addresses here, and those are organized in this fashion. You have the IR out, which bits 25 through 21 is your S address, 15 through 11 is your D address, 16 through 20 is your T address. Typically, S and T addresses are your operands to your ALU, and D address is usually the write back. And those are controlled by MUX, and the MUX is controlled with our finite state machine.
So that MUX is internal.
Yes.
So sometimes, yeah, got it.
So now that we've discussed the CPU, we're going to talk about the data memory and the I/O modules. So data memory, resources are scarce. We only have 32 registers in the CPU. Therefore, we have data memory. It's organized as 4096 by 8 byte addressable, which is basically 32K. It's a big Indian format, and it interfaces with the CPU. Similarly to data memory, you've got your I/O module. An I/O module is also a memory module. However, it interfaces with input and output devices such as your keyboard, your mouse, monitor. Now, the I/O module, nobody likes to be interrupted, but it's necessary. Ideally, there's an I/O ready signal between the CPU and the I/O module. However, for our design, we don't implement this signal because we are assuming that data is available within a few clocks and there's no wait states.
A few clocks? What do you mean a few?
Well, it depends on that.
It depends? What's it depend on?
Well, you need some clocks to read it and then write back.
So what's your assumption again?
So we're assuming that
There are no
data,
wait states.
no wait states.
No wait state. Okay, good.
Moving further down, here's a diagram. We've got our CPU and both of our memory modules, data memory and input and output. Ashish will discuss the signals taking place.
So again, just again a quick overview. What the CPU is interfacing with your two main memory modules. You have the control signals on top. You have the chip select. You have the read and write, which is the same for both modules. Okay, and then we have the address for both memory modules. We have data in and data out for both memory modules. Okay, and then on the I/O memory, we have implemented an interrupt request that's generated by the I/O module to the CPU, and an interrupt acknowledged from the CPU to the I/O module, and an interrupt in from the CPU to the I/O module. And here we have a dotted line here on the left side. Again, we're assuming that there are no wait states, but in reality, to access data memory takes hundreds of cycles. So that signal is not really implemented in our design, but it's necessary for it to work. And similarly, the I/O ready signal.
So that summarizes our hardware. We're now going to talk to you guys about our enhancements. As we mentioned before, we did a total of 6 enhanced instructions: NOT, NAND, XNOR, SQR, JC, and JNC.
So this is, we took, our state machine wasn't very complicated. We only had 76 states in there because we were just using the base R-type instructions and some J. So we had a total of 76 states. As we discussed earlier, we were looking at the decode state, we're looking at bits 26 through 31 to be 1F, which was our enhanced key. If those bits were 1F, then we would go ahead and look at what the lower 6 bits were. And we decided to put NOT at 0, 0, NAND at 0, 1, XNOR at 0, 2, squared at 0, 3, JC at 0, 4, JNC at 0, 5.
So let's begin with our NOT instruction. This is our instruction memory, and this is our register dumps. As you can see, that is our source code Verilog hardware design. And what we're doing here is we're going to walk you through how this NOT instruction executes. So for the NOT instruction, if you notice, Louis Ori is loading that value into register 1, which we can verify by looking at a register dumping. And register 1 indeed matches with what it should be. And the NOT instruction, what it's doing is it's knotting the value stored in register 1 and placing it into register 2. If we calculate that response, knotting that value gives us this answer, which should be stored in register 2. That indeed matches, verifying that our NOT instruction is working.
Also, I did want to point out before we hit the NOT, we did write to register 3 there. We did initialize register 3 to have the 5FF, FF00.
It's going to be in the next slides.
So here's the NAND instruction. So what the NAND does is it basically takes, it's an AND, but the results are not it. Okay, so in this slide, we basically have taken R2, which was the previous results of the NOT. You can see the R2 is 55FFFF00. Now we're taking R3, which we have previously initialized. Okay, 55FFFF00 here. And then we're going to go ahead and add those results. This is a snippet from the calculator. This we just decided to include this just to show you that it works. So that is your AND if you do the AND between those registers. And then if you go ahead and NOT those, that will be a result, and those results are supposed to be stored in R4. And indeed, our results are AA0000FF. So that shows that our NAND is functioning.
Another instruction, which was an enhanced instruction, is XNOR. Similarly to the previous slides, this is an instruction memory, register dumps, and source code Verilog hardware design. If you notice, register 1 has already been initialized, register 3, and the XNOR instruction is taking the value stored in register 1, the value stored in register 3, it's XORing them, getting the result, and knotting that result, and placing it into register 5. Now let's take a look at the calculation. So if you take register 1, XOR it with register 3, you get this value. That value knotted turns out to be this answer, which should be in register 5. So let's see. Register 5 does include the same value, which verifies that our XNOR instruction is functional.
Okay, so this is something I thought of and I should have thought a little bit more about. Just taking a number and multiplying by itself squared, which is not native, again, to MIPS. The issue that I ran into, I wasn't displaying the full result. You take a 32-bit and multiply by itself, you need more bits to display the result. But anyhow.
But you've got high-low.
I do, but I'm not just displaying it. I do have the full results. I'll explain.
Okay.
So what's going on in this instruction is we're taking R1 here, which we know had that value, the AA00, 00AA value, and we're multiplying it by itself, hence squaring the number, okay? If you multiply that together, these are your lower 32 bits, okay? This is not the full answer, okay? And unfortunately, I didn't, I should have displayed it, and I realized it later on. And so that result is being displayed there in R6, okay? So we basically took the T side and multiplied by itself, stored the value. We did store it into the high and low. Obviously, we're only displaying the low, not displaying the high.
What might be a solution for that, though?
which is.
I mean, in other words, processors do that and they've got a double-length product. Where do they put the double length back in the register file? So in your example, you specified R6, so it could be implicit that you're gonna write to both R6 and R7.
Yes.
That's pretty
That
typical.
would be,
Yeah,
be a
that'd be
solution
pretty
to
typical.
display that.
Yeah, that's just
Yeah, I
implicit.
thought of that later on, I was like.
That's okay. Yeah.
Moving on to a little bit more interesting instruction, we've got a JC, jump if carried. Here's our IMM and here's our registers, outputs. If you notice, here, register 7 is being loaded with all Fs, and we can verify that that is the case looking at a register dump. Little down the line, there's an addition instruction, which is adding register 7 to itself. Let's take a look at the calculation. So what it's doing is it's adding register 7 to itself, which turns out to be this answer. This answer has a carry bit. That carry bit sets the carry flag, which indeed will be used for the JC instruction in order to jump to label 1. Therefore, at that time, we're going to skip the scope because we're jumping to label 1. Now, the way that we verified that this works is we had a fail or pass. The fail flag would show a value of 1 in register 14, and the pass flag would show that would execute the instruction for add immediate, putting a value of 2 into register 14. If we look at register 14, it does have a value of 2, which shows that we have passed and are in label 1.
Good.
Okay, so this is the same type of instruction as checking the flag and seeing if it's set or not. This is jump on not carry. That's what a jump on not carry does. Here it's going to check to see if the carry flag is set. How it's checking that, it's looking at, we're doing a subtraction between 7 and 3, R7 and R3, register 3 is storing the results in R9. As you can see those highlighted registers. And that is the result of that subtraction there. And then there's no carry flag set. So again, our pass fail on this was, we were going to load a 1 if it failed, because obviously if there's no carry flag, we wanted to jump to the label. If it failed, it was going to write a 1. If it passed, it was going to write a 2 to R15.
And it passed.
So in this case, it passed, and we have R15 at 2. So that's working.
Same here.
1 minute.
And actually, that concludes our Me JPass 32 MIPS processing.
Excellent job.